Thanks all. Thanks also for the invite to come and speak here today. And thank you everyone for coming along to this session. Yeah, my name's Callum. I'm from Monzo, somewhat obviously. And yeah, I'm going to talk for the next 35 minutes about how we're approaching fraud detection in a slightly new way, in a slightly exploratory way at Monzo. I went from trees to MLPs because it rhymed, but that's kind of not exactly what happened. But yeah, we'll go through it. But before we get into that, a bit about me. I'm a lead machine learning scientist at Monzo. I work in our financial crime collective, working mostly on exploring different techniques for detecting fraudsters, detecting financial criminals, and yeah, generally exploring lots of cool machine learning techniques for doing that. Prior to being at Monzo, where I've been for about 18 months now, I was a researcher in biotech, cybersecurity, defense, and also materials discovery. So I have to start with a little bit of a disclaimer. Fraud detection is a fairly sensitive topic. And this is because fraudsters are always looking for new ways to scam our customers. And we are always looking for new ways to try and detect them. So as a result, I can't really go into details about specific kinds of features that we use or exactly how some controls work and so on. And I apologize for that in advance. So if I answer a question with, I don't know, that's classified or something, I apologize. But hopefully there's still lots of interesting information in this talk that you'll find interesting. So let's set the scene a little bit. Very recently, I think just this month, UK Finance issued their most recent fraud report. They do an analysis of fraud and all its typologies across the UK finance sector. And they said that in 2024, about 1.1 billion was stolen by fraudsters in the UK. And that is a decrease from 1.2 billion in 2023. But that's still a really significant number. Sure, it makes up a tiny fraction of the total amount of money that moves around the UK financial system every year. But for anyone in this room or anyone who knows someone who's been a victim of a scam or fraud, you know how much of a devastating effect these kinds of things can have on people's livelihoods and well-being. So we ultimately really want to stop this number and make this number as low as we possibly can. And we're doing what we can to do that. Currently, the same report estimates that about 64 pence of every pound of fraud is prevented by fraud detection controls. So we're doing OK, but we want to do an awful lot better. So if anyone doesn't know, what do I actually mean when I say fraud? Well, we can take the sort of FCA definition, the Financial Conduct Authority. They define it as a kind of transfer of funds where a payer has been coerced or deceived into making a payment that they think is for legitimate purposes. To make that more concrete, maybe your card was skimmed at an ATM and someone steals your details and makes payments. Or you think you're making a payment to a legitimate merchant to pay for goods or services, and they never arrive or you never receive them. And that all counts as fraud. And what you can see from that is that there's loads of different ways that fraud can happen. It's really diverse, always changing, and we end up in this constant kind of game of cat and, well, finger in this case, cat and mouse, where we're constantly trying to detect the fraudsters. They're constantly trying to evade the controls, and this process just repeats. But fraud detection is absolutely vital. It's not just a regulatory constraint. It's something that we ultimately want to do to reduce customer harm and, of course, prevent the sort of wider societal impacts that can happen when there's a breakdown in trust in the banking system. So fraud detection is really, really vital, and that's what we currently work on and what we look at in financial crime at Monzo. So how might this kind of system, fraud detection system, work at a high level? We can follow this kind of process. Imagine a Monzo customer goes into Tesco and is using their card to pay for some goods, and they are tapping their card. Well, this is the customer initiating some kind of transaction, and we have to do a whole load of stuff before we say that we're going to let that transaction go through. The first thing might be curating a bunch of features about this transaction. Could be about the merchant, could be about the individual, or various other features. And this all happens in our feature store. And we pass those features to some kind of machine learning model or rule that ultimately has to predict what's the likelihood that fraud is occurring here. Now, we don't just have to use models. We can have second layer decisioning logic that we apply in addition to the results of these rules to say, given the probability of fraud and various other conditions, do we want to apply some kind of intervention? And if we do, then we'll apply that action to that transaction. So for example, I'm sure it's happened to everyone in this room, you go to tap your contactless card, and it says, oh, please enter the card for chip and PIN. That could be for fraudulent reasons. It could be because it's been a while since you haven't done it. But in general, that sort of process happens, and we apply some kind of friction there. Most importantly, this has to happen really quickly. We have to make this decision typically in the order of about 950 milliseconds to do a big end-to-end process. So we don't have a lot of time to make very complicated sort of reasoning logic in this pipeline. So for this talk, I'm going to focus mostly on what happens in this red kind of circle. How do we teach machine learning models to make a prediction about the likelihood of fraud as best we possibly can? So let's start with the old school way, very non-LLM focused methodology. One way, let's treat fraud detection as a binary classification problem. Simple yes, no. Is this transaction fraud or not? To do this, we could take one of your classic Python libraries and throw some data at it, right? XGBoost, like GBM, scikit-learn, etc. What would we need to do this? We need a data set, primarily. So when our customers are defrauded, they send us what we call fraud reports. They tell us, hey, Monzo, I don't recognize this transaction. Please investigate. And that gives us, over time, a pretty big set of labels, positive labels in this case, from which we can train a model. There are caveats to that. Often, some customers never report fraud at all. Other times, they don't report fraud until 3 months after the fraud happened. Or sometimes it's not really fraud at all. It could just be a dispute that's happening between a merchant and our customer. So we have to take our positive labels with a bit of a grain of salt, but let's ignore that for now. Let's just say we get a good set of positive labels from our customers reporting fraud. And of course, we have all the transactions that happen that aren't fraud as our negative labels. Machine learning scientists, data engineers, data analysts, data scientists, we can all go in and then start doing some exploratory data analysis, engineering features, trying to find that signal that's predictive of a certain type of fraud. We can build those features, and we can train our model. Sounds kind of easy. And to be honest, this actually works great, right? These classic models are fantastic. They're quick to use. They work out of the box, amazing on tabular data. Their inference times are quick, so we can put them into that prediction chain. Yeah, it's a great solution. We could just stop here. But there are some limitations with that. And one typical limitation is that we often design those features to work for a specific type of fraud that we're kind of trying to catch. So if we have n types of fraud, I need n sets of features. I need n models, which I then need to maintain, monitor, govern, retrain. And so we build up this sort of big overhead over time of more and more models that we have to manage. The second thing is that fraud is really rare. It's a really imbalanced problem, about 1 in 10,000 transactions, something like that. But some types of fraud are even rarer than that. So you imagine if you've got a type of fraud that emerges 1 in a million, it's actually hard to get enough positive labels to train a dedicated model for that particular type of fraud. So often, that results to us having to group types of fraud together, which we then train a model on top of a group of labels, which naturally actually isn't a strong suit of these kind of classic tree-based classifiers. So it's a great option, but it's not perfect. And so we want to see if we can find a better way. And as I say, this kind of leads us into this classic fraud detection cycle, where at the start, we start to see that a new type of fraud or scams are happening. We receive more fraud reports. We analyze those patterns. We might deploy kind of tactical rules or models to kind of dampen that initial spike. And that helps us build labels over time from which we can train a model. And then the fraudsters say, oh, that's not working anymore. Let's try something else. And the process just repeats. So it's kind of a reactive approach to fraud detection. Is there another way? Well, in our squad at Monzo, we started thinking, would it be great in an ideal world if we had one model that would just detect all fraud? Maybe that's a little bit optimistic. I'd accept 2, maybe a couple. But in general, we thought, can we borrow ideas from domains where models have shown this amazing ability to work well across different domains and typologies, like natural language processing, computer vision, etc. And that's particularly the realm of kind of deep learning, right? So we thought, let's start with this hypothesis. What if we could just train one model? And then speaking to experts in the field, people who really work on fraud features, we sort of realized this thing that there are 2 types of fraud features. One that I'm calling general fraudiness. These are types of features that predict fraud that are common across lots of different types of fraud, subtypes of fraud. Could be investment fraud, impersonation scams, etc. And those features occur kind of ubiquitously. Then there are specific fraudulence features. These kind of features that really indicate the type of scam or the type of fraud that's occurring. Typically, when we train these tree-based models, we're looking at the latter. We're looking for those really specific signals that predict a specific type of fraud. But if we want to be more proactive in detecting fraud, we also need to learn from those general features. We need to have a model that's aware of the general patterns of fraud so that when something new comes along that doesn't fit these specific fraudulence features, it can still generalize and say, well, I think this still looks pretty fraudy. So the kind of idea here is a model that's aware of both of these types of features should be a better generalist. So kind of one model to rule them all, if you like. Now, one type of machine learning that really lends itself to this idea of both general and specific fraudiness is called multitask machine learning. In multitask machine learning, we take a single model and we train it to do multiple tasks at once. And these tasks are in some way related. We'll make this concrete with an example that's completely unrelated to fraud. Let's say I want to predict the properties of fruit, like the taste properties of fruit, based on how it looks. So we have apples, bananas, lemons, melons, etc. And my input layer, and these layers are just classic feed-forward neural network layers, I have some features, color, shape, size, etc. And then I put this through this kind of core set of layers. These are shared representation layers that effectively we're trying to learn here, what I'm now calling general fruitiness. We're trying to learn patterns that are common across all fruits. And then from that general shared layer, I'm going to try and predict I'm going to have some other heads that are going to try and predict particular properties of the sort of taste of that fruit. So we could try to say, let's predict the calories, the texture, and the sweetness of these fruits at once. And you kind of see that in some way those tasks are related. There should be some kind of idea that maybe the calories a fruit has is directly related to how sweet it is, and in turn that probably has some relation to the texture. So these are not completely distinct tasks. They share certain patterns that should help us make some kind of good quality prediction. So the key idea here is that by learning these general representation layers, we should be able to then make multiple good predictions at once. And this gives the model a better understanding of what a fruit is than if we trained 3 separate models for each of these particular tasks. What if we did the same for fraud? So exactly the same idea, but instead of giving fruit properties, we're going to give transaction properties. We're going to input some features about a transaction, put them through some general shared layers again. This time, instead of general fruitiness, we're going to learn general fraudiness. And then we're going to do some task-specific heads. We might predict whether or not the transaction is fraud. That might be a good one for fraud detection. The payment method, it could be things like the type of fraud that's happening, or all kinds of other tasks that we could come up with that are somewhat related, but not directly the actual target that we're trying to get, which is always one of the main heads. And then we can optimize this using some classic joint loss function where we weight each component of the loss, and we optimize using classic gradient descent, all implemented in PyTorch. OK, so this is kind of the idea. Why might this work in theory? The whole principle of multitask learning is to increase generalization by learning from multiple similar tasks simultaneously. And that's great because really the kind of idea of how that works is that A, we add more labels, because each one of these other tasks that we've added has its own set of labels. So when we were kind of limited in positive labels for the fraud-specific tasks, for all our other tasks, we might have a full set of labels for those, or a much more balanced set at least. This then gives the model the ability to combine features across those tasks and make better predictions on the whole. This is still the theory. The other great thing about this is that it can enable us to actually really get an idea if the model truly is learning general and specific features. We can extract the embeddings from the intermediate layers of this model and see what it's learning using classic visualization techniques. And the theory of this is that then, compared to like 3 separate task models, for example, we get faster convergence because the model is now using the sort of structured representation of the data to make better predictions for all the tasks, which should, in theory, converge faster. But there are problems. Now we have all kinds of issues around which tasks do I pick? How do I optimize their contribution to the loss? I need accelerated compute, and I need to probably spend a lot longer training and optimizing these models. So I certainly can't just pull this out of scikit-learn, run it, and ship it like I can with a tree-based model. So there are limitations, but in principle, the theory is good. So we wanted to test this. All very good, all very well and good having this theory, but we need to test it. The sort of test bed we wanted to look at is actually a type of fraud that is really an umbrella term for lots of different types of fraud. unauthorized card fraud, it's called. And this is a case where a card payment is being made, but the person who owns that account isn't the one who authorized that payment. So it could be that your card has been stolen. It could be that some merchant has initiated a transaction, like a standing order, for example, or it could be some kind of theft or account takeover situation. This really lends itself to the idea of multitask learning because there are actually lots of subtypologies here. There are lots of distinct ways that unauthorized card fraud can happen, but we tend to clump them together because it's sort of convenient and it gives us a lot of labels. But really, there are lots of different ways we could detect all of these individual types. So it kind of lends itself to this idea that maybe there are general features that are shared across all types of unauthorized card fraud, but also specific features to each individual typology. Next, it's actually a really important problem area. 90% of all fraud reports received by us, by sort of the number of reports, are related to unauthorized card fraud and makes up about 50% of the total transaction amount of fraud that we observe. So fairly significant. It would be remiss of me to talk about results without sort of going about metrics. So obviously, we want to catch as much fraud as we possibly can, which lends us to this idea of recall. Let's maximize as much fraud we can detect as possible. But I'm sure customer experience is, of course, an extremely important thing because not everyone wants the frustration of constantly having to go through several layers of friction just to make a card payment. So we need to also make sure that we're not just blindly applying frictions to everyone's transactions. So it kind of lends you to almost like recall at K type metrics, ranking style metrics where we want to make sure that we're maximizing our recall whilst minimizing the customer impact. OK, how are we going to test this theory? So we've got unauthorized card fraud. We've got a set of labels, fraud reports that we've received. We've got all the negatives. How are we going to prove that multitask learning, or this idea that multitask learning should be good, actually works in practice? So what we're going to do, we're going to train a baseline model. I'm going to take one of those classic gradient-boosted decision trees from one of those classic Python libraries, and I'm going to train it on the same data set. I also probably could ask the question, well, is it the multitasking that's working, or is it just the fact that you're using deep learning? So I'm also going to take a vanilla deep learning model and train that as well. We're going to train a multitask model with various tasks, and then we're going to compare their performance overall on all unauthorized card fraud, but also on the subtypes. So you can imagine we might do some stuff like holding out certain types of fraud from the model and seeing how the different types of model generalize to the new types of fraud. We're also going to take a look and see if our hypothesis is true that the embeddings or the representations learned by multitask models actually represent general and specific fraudulous features. Headline result. I'll start with the headlines. This plot shows a distribution of performance between our two main contenders here. The multitask model is in blue, the classic light GBM model in purple. And these are what we call bootstrap distributions. So effectively what we do is we gain a sort of distribution estimate of model performance over a 3-month period by effectively resampling the data set and recomputing the metrics. And what we can see from looking at those distributions and the performances is that we get a statistically significant uplift in recall in this case, which is great. That's overall, we could say job done, amazing, ship it. And that's a really important result because we know that this gives us a good, strong indication that multitask models are actually improving. OK, those of you who are thinking it's just the deep learning model that's done well here. The deep learning model, actually, the classic vanilla MLP is actually off the chart. So it's not 0 on the x-axis here. It's like much worse in this case on this specific task. And that's not too surprising. Anyone who's tried to beat tabular models with classic feed-forward neural networks, it's very, very hard to do. So overall, results look pretty good. What is then this multitask model actually kind of learning? Why is it doing better? And can we get any inference about what the model's actually learning to make it actually improve over the light GBM model? So what we did, we extracted the embeddings, learned these are transaction level embeddings, learned at the 2 different layers that we're interested in this model, that shared representation layer, and also the kind of fraud-specific layer head that we have in our model. And if we plot those transaction embeddings using PCA in 2D on the left-hand side here, we color them by whether or not fraud was or wasn't reported, we get quite an interesting result. So the model, as you would expect for the final sort of layer of a deep learning model, is learned to do a pretty good sort of almost linear separation between the 2 classes. Great, it's being predictive. But what does this actually mean? It means we have embeddings that enable us to do sort of similarity checking. We can start to see, hey, show me this transaction that's similar to this fraudy one. And we can start to investigate then, why are these purple dots occurring in the sort of yellow strand? Is there something fraudy about them? Are they mislabeled? Are we missing some features? It gives us a real ability to kind of interrogate the kinds of features that the model's using for prediction there. On the right-hand side, we have the kind of general fraudiness representation. So I've extracted from that shared layer. And interestingly, the coloring here actually represents the payment method that was used. And that wasn't actually a feature of the model. So the model's kind of learned to do a pretty good distinction between the different payment mechanisms used for these transactions all by itself, which is kind of interesting. And that's part of the multitasking idea, is that we can learn a kind of structured representation of these embeddings by changing our tasks. And interestingly, the payment method is one of the tasks that we used to train the model. I guess most importantly then, the question is it true then that you're getting better generalization from this model, or is it just, I don't know, overfit to your particular use case? This plot shows a comparison between the number of kind of interventions we apply per week against the recall of the model. So you get this kind of curve. And what we did in this test was hold out a specific type of fraud and train the models on all other types. And again, what we see is quite stark. The multitask machine learning model was far better at generalizing to this unseen type of fraud than either the light GBM or the MLP, which is great, right? This gives us really good indication that if this new type of fraud emerged today, which model would be better at trying to detect it? It would be the multitask model in this case. So that kind of gave us the most signal that this idea really, really does work. So there's kind of, probably a few key findings, but I think the main one is big improvements, right? I think the best test scenario, we saw sort of 30% relative improvement. And that's really encouraging for us. It means that this multitask machine learning avenue looks like a really promising avenue for improving the recall of our models on an overall basis. But probably more important is that performance on rare or held out fraud subtypes. What's critical there is that if we want to break that fraud detection cycle, we need to be more proactive in trying to identify types of fraud. And so just having the ability to be more confident on new types of fraud means that we're already getting ahead of the scammers, breaking that cycle, reducing the amount of fraud that our customers experience, which is ultimately what we want. Perhaps then the big sort of elephant in the room is, well, you said that you have to do all of this in like 950 milliseconds of latency. How can you fit a deep learning model into that architecture? And that is a big sticking point. So what we want to do here was test, what if we took the embeddings learned by the multitask machine learning model and fed that to a light GBM model instead, right? So now we're getting the speed of inference of a light GBM model with the predictive performance in theory of these embeddings. And actually, that gave us the best overall performance. So we've kind of combined the really discriminative predictive power of light GBM models or tree-based models with the predictiveness that we've learned through almost like a pre-training task in terms of the multitask objective. So that actually gives us a really great opportunity for deployment and getting these models into the payments path. Yeah, so to really kind of recap that summary and that particular overview. So multitask learning looks really promising for this task of fraud detection, particularly on rare and emerging subtypes of fraud. We can utilize embeddings generated from this to do things like label improvement, similarity search, and training more specific downstream models. We get better generalization, and we think that this will work in a deployment sense with no increase in latency. That's it from me. Big plug, we are hiring across many roles in tech and data. So if you're interested to come and work on some interesting problems in this space and others, yeah, come and see us at the Monzo booth. We'll be happy to chat and give you a coffee and maybe some swag. Thank you so much.